You were taught something simple about planets. They have structure, a solid core at the center, surrounded by layers that gradually become lighter as you move outward. It's clean, predictable, almost comforting. Every diagram you've ever seen shows the same thing. A neat cross-section, like a perfectly layered cake. Jupiter, the largest planet in our solar system, should follow that rule better than anything else. Bigger planet, stronger gravity, more defined structure. That's what everyone expected. But that expectation was wrong. When NASA sent the Juno spacecraft toward Jupiter, the goal wasn't to challenge our understanding of physics. It was supposed to confirm it, measure the atmosphere, map the magnetic field, estimate the amount of water, fill in the missing details, not rewrite the entire picture. Juno wasn't even designed to survive for long. Jupiter is surrounded by radiation so intense it can destroy electronics in months. Previous missions had already shown how dangerous it was. Instruments failed, systems degraded, the environment was unforgiving, and yet Juno kept going. Orbit after orbit, it dipped closer to Jupiter than any spacecraft before it. Flying just a few thousand kilometers above the cloud tops, it passed through regions that should have fried it completely. But something unexpected happened. The radiation was lower than predicted, not safe, but survivable. It was as if Jupiter itself had opened a narrow path, just enough for Juno to slip through. That one detail changed everything, because it meant Juno could keep collecting data, and the longer it stayed alive, the stranger the data became. At first, the images were already confusing. Jupiter didn't look like Jupiter anymore. The familiar bands that wrap around the planet seemed to disappear near the poles. In their place were massive cyclones, arranged in geometric patterns that looked almost artificial. Perfect circles, locked together, spinning in ways no one had predicted. If you didn't know what you were looking at, you might not even recognize the planet. It didn't match the picture we had built in our minds. But the visuals were just the surface. The real surprise was hidden deeper. Not in the clouds, not in the storms, but far below them. Juno wasn't just taking pictures. It was measuring gravity with extreme precision. Tiny fluctuations, almost impossible to detect, revealed something about the distribution of mass inside the planet. And that's where everything began to fall apart. Because what Juno found didn't match any existing theory, not even close. And once you understand what it discovered, you realize something unsettling. We didn't just misunderstand Jupiter. We may have misunderstood how planets are supposed to work. To understand why Juno's discovery was so shocking, you need to understand what scientists were expecting to find in the first place. For decades, there were only two serious theories about Jupiter's interior, and both of them seemed reasonable. The first idea was simple. Jupiter never had a core at all. It formed directly from a massive cloud of gas collapsing under its own gravity. In that scenario, the planet would be nothing more than layers of gas all the way down, getting denser and hotter as you go deeper, but never forming a solid center, just pressure, motion, and turbulence without a clear boundary. The second idea was almost the opposite. Jupiter started with a solid core made of heavy elements like rock and ice. As that core grew, its gravity became strong enough to pull in enormous amounts of hydrogen and helium, building the massive gas giant we see today. This model, known as core accretion, became the dominant explanation because it matched what we observed in other parts of the solar system. It made intuitive sense. Start with something solid, then build around it. Both theories had strong arguments, both explained certain observations, and for a long time, scientists debated which one was correct. But here's the important part. Even though they disagreed, they shared one assumption. Jupiter had to fit into one of these two categories. Either it had a clear core, or it didn't. There was no third option. No one was seriously considering that the truth could exist somewhere in between, because physics, as we understood it, didn't really allow for that kind of ambiguity. That's why Juno's approach was so different. Instead of trying to look directly at the core, which is impossible, it measured something indirect but incredibly powerful. Gravity, not just the overall pull of the planet, but tiny variations in that pull. If Jupiter were perfectly uniform inside, its gravity would also be perfectly uniform. But if mass is distributed unevenly, those differences create subtle changes in the gravitational field, and Juno was sensitive enough to detect them. As it orbited Jupiter, Juno constantly sent radio signals back to Earth. Scientists tracked these signals with extreme precision. When Juno sped up slightly, the frequency shifted. When it slowed down, the frequency shifted in the opposite direction. These tiny changes revealed how gravity was pulling on the spacecraft at different points in its orbit. And from that, scientists could reconstruct how mass was arranged deep inside Jupiter. What they expected to see was a pattern that matched one of the existing theories, a clear signature of either a solid core or a fully mixed interior. But that's not what appeared in the data. Instead, the signals suggested something far more complicated, something that didn't have a sharp boundary, something that gradually changed from dense to less dense without a clear transition. At first, it didn't even make sense. The models didn't fit. The simulations couldn't reproduce it. It looked like an error, but it wasn't. It was the first real clue that Jupiter was hiding something no one had predicted. At first, scientists didn't accept it. They couldn't, because the data Juno was sending back didn't just challenge one theory. It broke both of them at the same time. If Jupiter had a solid core, the gravity signal should show a clear concentration of mass at the center, a sharp change, a boundary, something you could point to and say, that's where the core begins. But that boundary wasn't there. The transition was smooth, stretched out, almost blurred. On the other hand, if Jupiter had no core at all, if it were just gas all the way down, then the mass distribution should be more uniform. The gradients should follow predictable patterns. But they didn't. The data showed something uneven, something layered, but not in a clean way, something structured, but not solid. It didn't match either model. So scientists did what they always do. They assumed the problem was with the data. Maybe the instruments were off. Maybe the calculations were wrong. Maybe there was some interference they hadn't accounted for, because it's easier to question your measurements than to question decades of theory. But as more data came in, the pattern didn't go away. It became clearer, more consistent, more impossible to ignore. The signal repeated across multiple orbits, from different angles, under different conditions, and every time it told the same story. Jupiter's interior wasn't clean. It wasn't divided into neat layers. It didn't have a well-defined core. Instead, it looked like the heavy elements that should have formed a solid center were somehow mixed into the surrounding hydrogen and helium. Not fully dissolved, not fully separate, but spread out over a huge region. A gradual transition instead of a sharp edge. Imagine dropping ink into water and watching it slowly diffuse. At first, there's a clear boundary. But over time, that boundary disappears. The ink doesn't vanish, it just becomes part of the whole. That's the closest analogy we have. Jupiter's core isn't gone, it's smeared. And that's a problem, because the entire process of planet formation depends on separation. Heavy elements sink, light elements rise, gravity sorts everything into order. That's how structure emerges. That's how planets differentiate. But Jupiter doesn't seem to follow that rule. Its interior looks like something disrupted that process. Something prevented the heavy materials from settling into a compact core, or something broke that core apart after it formed. And here's where things get even more uncomfortable. If this only happened on Jupiter, you could explain it away as a rare event, a cosmic accident, something unusual but not fundamental. But the deeper scientists looked, the more they realized that Jupiter might not be the exception. It might be the clue. Because if our biggest planet doesn't follow the rules we thought were universal, then maybe those rules were never as solid as we believed. Naturally, the next step was to explain it. Scientists needed a mechanism, something that could take a normal planet with a solid core and turn it into this strange, diffuse structure. And there was one idea that seemed promising, a massive collision. Early in the solar system, everything was chaotic. Planets weren't stable yet. Objects collided all the time. Some of those collisions were catastrophic, large enough to reshape entire worlds. So the theory went like this. Jupiter formed normally with a solid core. Then, at some point in its early history, another large planetary body slammed into it. Not a small impact, but something enormous, big enough to disrupt the core, to break it apart, to mix it into the surrounding layers. That would explain the fuzziness. It would explain the lack of a clear boundary. It would explain why Jupiter looks the way it does today. At first glance, it seemed to fit, so researchers tested it. They built detailed simulations, recreating the conditions of the early solar system. They modeled massive impacts, varying the size of the incoming object, the speed, the angle, the composition. They ran scenario after scenario, trying to produce the exact structure Juno had observed. And in the beginning, it looked promising. The impact would shake the planet violently. The core would be disrupted. Heavy elements would scatter into the surrounding gas. For a brief moment, the model resembled what Juno saw, but then something happened. Given enough time, the system corrected itself. The heavy materials began to sink again. Slowly, but inevitably, gravity reasserted control. The core started to reform. The sharp boundary returned. The fuzziness didn't last. Every simulation ended the same way. No matter how violent the collision, no matter how extreme the conditions, the planet always settled back into a more traditional structure. A dense core surrounded by lighter layers. It refused to stay mixed. It refused to remain fuzzy. And that was the problem, because Juno's data showed that Jupiter's interior is still fuzzy today. Not temporarily, not in transition, but stable. Whatever happened inside Jupiter, it wasn't something that naturally resolves over time. It's something that persists, something that resists the normal rules of planetary physics. This forced scientists into an uncomfortable position. The collision theory, as elegant as it sounded, didn't actually work. It explained the initial disruption, but not the long-term stability. And without that stability, it couldn't match reality. So once again, the explanation failed. And once again, the mystery deepened. Because now it wasn't just about what Jupiter looks like, it was about why it stays that way. Why the heavy elements don't simply sink back to the center. Why the structure remains blurred instead of separating into clean layers. Something inside Jupiter is preventing that process. Something is keeping it mixed. And at this point, the question changes. It's no longer what happened to Jupiter's core. It becomes something much more fundamental. What if Jupiter didn't lose its core at all? What if it never formed the way we think it did in the first place? That possibility is far more disruptive than it sounds. Because if Jupiter never formed with a clean, solid core, then the core accretion model, the one that has been used to explain gas giants for decades, starts to fall apart. That model depends on a simple sequence. First, small particles collide and stick together, forming larger and larger bodies. Eventually, those bodies become massive enough to create a solid core. Then, once that core reaches a critical size, its gravity pulls in vast amounts of gas, rapidly forming a giant planet. It's a step-by-step process, logical, predictable, and most importantly, it works well in simulations. But Juno's data suggests that Jupiter doesn't look like the end result of that process. There is no clear boundary, no dense, compact center. Instead, the heavy elements are spread out over a huge region, blending gradually into the surrounding gas. It's not what you would expect if everything had formed in neat stages. So now scientists are forced to consider a different idea. What if the formation of gas giants isn't clean? What if instead of building a solid core first and then adding gas, everything happens at the same time? Imagine a collapsing cloud where gas and heavier materials are mixing continuously, never fully separating, never forming a sharp boundary. In that scenario, a fuzzy core isn't a problem. It's the natural outcome. The planet doesn't have a clear beginning or center. It just gradually becomes denser toward the middle. That idea is messy. It doesn't give you clean diagrams or simple layers, but it might actually match what we're seeing. And here's where it gets even more interesting. Jupiter isn't the only gas giant in our solar system. There's also Saturn, slightly smaller, less massive, but formed from the same primordial material. If Jupiter is strange, Saturn should provide a comparison, a control case, something to confirm whether Jupiter is unique or part of a pattern. And for a long time, Saturn seemed more normal. Its structure was less well understood, but nothing about it obviously contradicted existing theories. It didn't raise the same red flags until scientists started looking closer. Using data from the Cassini mission, researchers began analyzing subtle waves in Saturn's rings. These waves aren't random. They are caused by vibrations deep inside the planet, similar to how earthquakes reveal the structure of Earth's interior. By studying those patterns, scientists could infer how mass is distributed inside Saturn, and what they found was surprisingly familiar. The data didn't point to a sharp, well-defined core. Instead, it suggested a gradual transition, a region where heavy elements are concentrated but not separated cleanly from the surrounding layers. In other words, Saturn also appears to have a fuzzy core. Now, it's no longer a single anomaly. It's a pattern. Two massive planets formed in the same system, both showing the same unexpected structure. That makes it much harder to dismiss, because coincidences happen once. Patterns demand explanation. And if both Jupiter and Saturn form this way, then whatever process created them is not rare. It's fundamental. Once you accept that Jupiter and Saturn both have fuzzy cores, the implications start to spread outward, because these two planets aren't just random objects. They dominate our solar system. Jupiter alone contains more mass than all the other planets combined. It formed early, likely before the rest of the planets had fully taken shape. That means whatever process created Jupiter didn't just affect one planet. It influenced everything that came after. Its gravity shaped the orbits of other planets, redirected comets, and controlled the distribution of material across the solar system. So if Jupiter formed in a way we don't understand, then the entire history of the solar system becomes less certain. And it doesn't stop there. Over the past few decades, astronomers have discovered thousands of exoplanets orbiting other stars. Many of them are gas giants, similar in size or even larger than Jupiter. These planets were often explained using the same core accretion model: build a core, then accumulate gas. It was assumed to be a universal process, something that happens the same way everywhere. But now that assumption is under pressure. If the gas giants in our own solar system don't follow that model cleanly, why should we expect distant planets to follow it at all? The fuzzy core might not be an exception, it might be the rule. This creates a deeper problem. Not just about Jupiter, not just about Saturn, but about the reliability of our models. In science, models are supposed to simplify reality while still capturing the essential behavior of a system. But sometimes they become too clean, too idealized. They start to describe a world that behaves more neatly than the real one does. And when new data arrives, it exposes that gap. That's what Juno did. It didn't just add more detail. It revealed that the underlying assumption, the idea of a clearly defined core, might not be valid in the first place. And yet, even with this new understanding, there are still pieces that don't fit, because Jupiter is not just unusual in its structure, it's also unusual in how it behaves. Its magnetic field, for example, is one of the strongest in the entire solar system. Generated deep inside the planet, it extends millions of kilometers into space, forming a massive magnetosphere. For years, scientists believed they understood how this worked. The motion of electrically conductive material inside the planet creates a dynamo effect, producing a magnetic field. It's the same basic principle that generates Earth's magnetic field, just on a much larger scale. But Juno's data complicated that picture as well. Because if Jupiter's interior is partially mixed, partially stable, and not fully convective, then the flow of material inside the planet becomes harder to predict. And if the flow is unpredictable, the magnetic field should be chaotic. But it isn't. It has structure, it has patterns, It even has asymmetries that don't match simple models. In some regions, the magnetic field is much stronger than expected. In others, it behaves in ways that are difficult to explain. So now we have two problems instead of one. We don't fully understand Jupiter's structure, and we don't fully understand how that structure produces the magnetic field we observe. To understand why this is so difficult to resolve, you have to think about what's happening deep inside Jupiter. At extreme pressures and temperatures, hydrogen doesn't behave the way it does on Earth. Instead of being a simple gas, it transforms into a strange state known as metallic hydrogen. In this form, it conducts electricity like a metal, allowing currents to flow through it. Combined with Jupiter's rapid rotation, this creates the dynamo effect that generates its enormous magnetic field. That part, at least in theory, makes sense. But the details are where things start to break down. If Jupiter's interior were fully convective, meaning material is constantly rising, cooling, and sinking again, then the motion of metallic hydrogen would be relatively uniform. That would produce a magnetic field that is more symmetrical, more predictable. But Juno's data suggests that large regions inside Jupiter are not fully convective. Some layers appear to be stable, resisting that vertical mixing, and that changes everything. Because now, instead of a single uniform dynamo, you may have multiple regions interacting with each other in complex ways. Some layers moving, others remaining relatively still. Some conducting electricity efficiently, others less so. This layered behavior could explain why Jupiter's magnetic field is so uneven. In certain regions, the field is far stronger than expected, concentrated into localized spots. In others, it weakens or behaves irregularly. One of the most striking discoveries from Juno was a region now referred to as the Great Blue Spot, where the magnetic field is unusually intense. It's not centered, not symmetrical, not what simple models would predict. It's as if the dynamo itself is distorted, shaped by internal structures we don't fully understand. And here's the key connection. That internal structure is directly linked to the fuzzy core. If the heavy elements are spread out instead of concentrated, they can create regions with different densities, different conductivities, and different flow patterns. These variations can disrupt the smooth motion required for a simple magnetic field. Instead of one clean system, you get overlapping processes, interfering with each other. The result is a magnetic field that looks more like a patchwork than a single coherent shape. But even that explanation isn't complete, because when scientists try to model this behavior, they still can't fully reproduce what Juno observes. The simulations get close, but not close enough. There are always discrepancies, features that don't match, patterns that appear in the real data but not in the models. It's like trying to solve a puzzle where some of the pieces are missing and others don't quite fit together. So once again, we're left in an uncomfortable position. We have better data than ever before. We have more detailed measurements, more precise observations, more advanced simulations, and yet the deeper we look, the less certain the picture becomes. Instead of simplifying the problem, Juno has made it more complex. It has shown us that Jupiter is not just a larger version of Earth, not just a scaled-up planet following the same rules. It is something fundamentally different, and whatever is happening inside Jupiter, we are only beginning to understand it. And just when it seems like the mystery couldn't get any deeper, Jupiter reveals something else, something visible, something violent, something that connects directly to everything happening inside the planet. It's auroras. On Earth, auroras are rare, delicate, and temporary. They appear near the poles, flicker for a few hours, then fade away. They are beautiful, but limited. On Jupiter, they never stop. They are permanent, massive rings of light, constantly burning at both poles, hundreds of times more energetic than anything we see on Earth. They don't just glow, they explode with energy. At first, scientists assumed the explanation would be straightforward. Charged particles from space interact with the planet's magnetic field, get funneled toward the poles, and collide with the atmosphere. producing light. That's how it works on Earth. Scale it up for Jupiter, and you should get a stronger version of the same effect. But once again, the data didn't match the expectation. The energy measured in Jupiter's auroras was far too high to be explained by simple models. The numbers didn't add up. There had to be an additional source of power, something else driving these enormous displays. Juno provided a crucial clue. The currents responsible for Jupiter's auroras are not primarily direct currents, like those on Earth. Instead, they appear to be dominated by alternating currents, constantly fluctuating, constantly shifting. That suggests turbulence, instability, a system that is not smooth but chaotic. And that chaos likely originates deep inside the planet, in the same regions responsible for generating the magnetic field. In other words, the auroras are not just a surface phenomenon. They are a reflection of the internal dynamics of Jupiter. And this is where everything connects. The fuzzy core, the uneven mixing of materials, the partially stable layers, the irregular flow of metallic hydrogen, all of it contributes to a magnetic field that is more complex than we expected. And that complex magnetic field, in turn, drives more chaotic currents, which produce more powerful and unpredictable auroras. It's not one problem. It's a chain reaction, each layer of complexity feeding into the next. Even Jupiter's moons play a role in this system. Io, the most volcanically active body in the solar system, constantly ejects charged particles into space. These particles become trapped in Jupiter's magnetic field, forming a massive torus of plasma around the planet. As Io moves through this environment, it generates enormous electrical currents, linking the moon directly to Jupiter's atmosphere. These currents feed into the auroras, adding even more energy to an already powerful system. It's not just a planet. It's an interconnected network with multiple components influencing each other. And the more we observe, the more it becomes clear that Jupiter is not a simple object. It's not just a ball of gas. It's a dynamic system, constantly evolving, constantly interacting with its surroundings. Every layer, from the deepest interior to the outermost atmosphere, is connected. And yet, despite all the data Juno has provided, despite all the measurements and observations, we still don't have a complete explanation. We can see the effects, we can trace the connections, but the underlying mechanisms remain just out of reach. And that might be the most unsettling part of all, because it means that even when we can observe something directly, even when we can measure it with incredible precision, understanding it is something else entirely. And just when it feels like we've reached the limits of what Jupiter can surprise us with, it does something even stranger. It challenges not just our models of structure or magnetism, but our understanding of weather itself. Because the storms on Jupiter don't behave the way storms should. On Earth, storms are temporary. They form, they evolve, and eventually they dissipate. Even the largest hurricanes lose energy and disappear. But Jupiter doesn't follow that rule. Some of its storms have existed for centuries. The most famous one, the Great Red Spot, has been observed for over 300 years, and it's still there. At first, scientists assumed this was just a matter of scale. Jupiter is bigger, its atmosphere is deeper, its energy sources are stronger, so naturally its storms would last longer. But that explanation only goes so far, because longevity isn't the only unusual feature. The structure of these storms is different. Their depth is different. Their energy distribution is different. And once again, Juno revealed something that didn't match expectations. When it flew directly over the Great Red Spot, it measured how deep the storm extended into the atmosphere. Scientists expected it to be relatively shallow, maybe a few tens of kilometers below the cloud tops. But the data suggested something far deeper, hundreds of kilometers, possibly more. That changes how you think about the storm entirely. It's no longer just a surface feature. It's a deep atmospheric system, rooted far below what we can see. And that raises a new question. What is powering it? On Earth, storms are driven primarily by heat from the sun and the movement of air masses. But Jupiter is different. It generates a significant amount of heat from within. Energy rising from its interior interacts with the atmosphere in ways that are still not fully understood. And if that internal heat is connected to the same processes responsible for the fuzzy core and the magnetic field, then the storms are not isolated phenomena. They are part of the same system. Juno also detected lightning on Jupiter, but not where it was expected. Previous models suggested that lightning should occur deep within the atmosphere, where water exists in liquid form. But Juno observed flashes at much higher altitudes, in regions that are far colder than we thought could support such activity. This led to the discovery of something entirely new: ammonia water storms. In these storms, ammonia acts like an antifreeze, allowing liquid droplets to exist at extremely low temperatures. These droplets collide, freeze, and form strange hail-like objects, sometimes referred to as mushballs. It's a type of weather that doesn't exist on Earth. A completely different system, operating under completely different rules. And once again, it connects back to the same idea. Jupiter is not just a scaled-up version of something we understand. It is fundamentally different. Its interior, its magnetic field, its atmosphere, its weather, all of it behaves in ways that stretch or break our existing models. And the more we learn, the more those models need to be adjusted or replaced entirely. What Juno has shown us is not just a more detailed picture of Jupiter. It has shown us that the picture we had before was incomplete in ways we didn't even realize. At this point, it's tempting to think we're close to an answer. After all, we have Juno. We have precise measurements of gravity, magnetic fields, atmospheric composition, and internal structure. We have better data than any generation of scientists before us. But the strange thing is, the more data we collect, the less certain the picture becomes. Not because the data is unclear, but because it reveals complexity we didn't expect. Instead of confirming our theories, Jupiter is forcing us to rethink them. And maybe that's the real story here. Juno was never meant to discover something completely new. It was designed to refine what we already believed. But instead it exposed the limits of those beliefs. The idea of a clean, well-defined core, the assumption that planets form in neat, sequential steps, the expectation that internal structures should be stable and predictable. All of these ideas worked well until we looked closely enough at a planet that didn't follow them. And Jupiter doesn't just break one rule, it breaks many. Its core is not solid but not absent. Its magnetic field is not simple but not random. Its storms are not temporary but not fully understood. Every layer of the planet challenges a different assumption. And when you put those challenges together, they point to something bigger. Not just a problem with Jupiter, but a gap in our understanding of planetary physics as a whole. Even now, scientists are working on new models, trying to explain how a fuzzy core can form and remain stable, trying to understand how partially stable layers interact with convective regions, trying to simulate the magnetic field in a way that matches what Juno observes. Progress is being made, but it's slow because each answer leads to new questions. Each solution reveals another layer of complexity, and that brings us back to Juno itself. This spacecraft was expected to last less than 2 years in Jupiter's orbit. The radiation alone should have ended its mission quickly, but against all expectations, it survived. Orbit after orbit, it kept sending back data, extending its mission, expanding our understanding, and in a strange way, its survival mirrors the mystery it uncovered. Because just like Jupiter's fuzzy core, Juno doesn't behave the way we expected it to. It was supposed to end, but it didn't. And that leaves us in a curious position. We have a spacecraft still out there, still observing, still collecting information, and a planet that continues to surprise us even after decades of study. We don't know exactly how long Juno will keep going. We don't know what it will discover next. But we do know this: Jupiter is not what we thought it was, and whatever is happening inside it is still not fully understood.